Okay, well, I haven't read it, so let's read it. A parking garage. That should be charges. A parking garage charges $30 per month plus $5 per daytime hour and 25 cents per hour during nights and weekends. 50 cents per daytime hour. Suppose Trent parks in the garage for 47 hours in March, and each of those are nights and weekend hours. Find an expression for Trent's March bill. Find the cost if Trent has 12 hours of night and weekend hours. Well, no wonder you didn't do it, because my gosh, that is a mouthful. Let's see if we can't tackle it together. I pray it's at least worded better on the Aspire, although they do like them some word problems. Okay. So no matter what, how much does he have to pay per month? $30. So I'm not going to put any variables for that. So we're trying to figure out how much money he's going to spend. So I'm going to use M for money. We're trying to figure out poor Trent's bill. We know he's at least going to pay $30. And then we're just trying to figure out the rest. So it's 50 cents per daytime hour. And 25 cents per hour during nights and weekends. So I'm going to put 0.50 for D, for meaning daytime. And then I'm going to do 0.25, and I'll put N for nights, but we know this could also be weekends. Are there any questions about my A, part A? And then it says, find the cost if Trent has 12 hours of nights and weekends. Well, I'm not even paying attention. There's something else I need to plug in first before I go crazy and do B. Do I know how many daytime hours he has? Okay, so let's see. What other numbers are in this problem that we haven't used? 47, and what other number? In part B? 12. So we somehow got to use that 47 and the 12. There's nothing wrong with our expression for A. That's great. But we've got to figure out an exact amount to tell Trent that he owes us on part B. So he's going to owe us some amount of money. For sure it's over $30. I'm going to leave that middle part blank. I'm going to go to the last part. How many nights and weekend hours did he have for that bill? It tells us. How many nights and weekend hours did he have for that bill? It does say H, but we'll read part B again. 12. So we got to plug in a 12 there. How many total hours did he have for this bill? Okay, so how many daytime hours did he have then? He had 47 total hours. 47 minus 12. He had 47 total hours. We know he did 12 hours of nights and weekends. So he was parked for 35 hours. Well, that would make sense. He's probably a businessman. This is his parking deck for his job or whatever. That makes sense. So we need to plug in a 35 for the daytime. Okay, you were okay with my expression. You're okay with why that's a 12. Does everyone understand why that's a 35? Okay, well, someone's got to use the calculator and figure that out for me, because I do not have my calculator with me this morning. That's 17.5. So 47.5 plus 3. So is it 50.5? So his bill for March is $50.50. Are there any questions about that bell ringer? Okay, that seems unrealistic here. We don't really have many parking decks. We do it like I know I do it like the hospital, but you have to pay it as you leave. So I'm not really sure this is the most realistic one for us in Alabama. But I could see somewhere where they're more tightly crunched, that might be a thing. Okay, maybe you'll be more alive with the notes. I want to do your translations first because they are easier. Genuinely, my logic, they're a little easier to handle. In fact, they're so easy, you're going to wish I had done them before I did rotations. I mean, reflections. Good grief, get it straight, Wisconsin. Okay, so, and because I'm trying to do the fast version, we might skip some of the blanks. You're just going to have to deal because we're trying to get through two things at once. So, obviously, a translation is a transformation that moves all points of a figure the same distance in the same direction. And we can use something called a translation vector. Can be used to describe the distance and direction of the translation. And all that means is, instead of an ordered pair, we draw it with arrows. And if we were wanting to say we went 5 left and 2 up, it still reads like an ordered pair. That 5 would tell you it's moving to the right because it's a positive 5, my bad. And the 2 would tell you it's moving 2 up because it's positive 2. If it was a negative 2 there, you would say pick the shape up, move it down 2. So while you've not heard the word vector before, it's really easy to read. You read it like you would an ordered pair. Okay, so let's read our first example. Can someone help me write the translation vector for our very first example? Before we even graph it, what is the translation vector? That is incorrect. What is wrong with what she's done? It does. It's down 4, so it needs to be a minus 4. Does everyone understand why it says down 4, so it needs to be a minus 4? It's reading just like a normal ordered pair. No, I appreciate that. I wish you'd make a tiny mistake all day. Okay, well, while you write that, we need to go ahead and graph those points. So let's see. A is at 1, 2. Over 1 up 2. There's A. B is at 1, 4. There's B. C is at negative 3. 1, 2, 3, 4. C. D is at negative 3, 2. What kind of shape is this? It's a rectangle. I'm putting my A down there instead. Okay, and I don't know if I was specific enough about this yesterday or not, but this first guy, because he was there first, we call him the pre-image. And what we're going to do next is the image. Now, do you have to know those vocab terms? No, but if you were to see them on a test, I'd still want you to know what to do. It says we need to move it right 2 and down 4. So we literally need to pick up this rectangle, move him right 2, move him down 4. So I'm just going to pick up the 1 point. I'll pick up D, because D's for dog and I like dogs. And I'll move it right 2, 1, 2, down 4, 1, 2, 3, 4. Now Kevin, if he likes counting, he can pick up each point and move it down 2, right 4, right 2, down 4. He can continue doing this. Or, Kevin's pretty smart. He understands it's still going to be a rectangle. He could probably go ahead and say, oh, well, C was 2 above D, so C prime needs to be 2 above D prime. D and A were that far apart, so let's make sure A stays that far apart. It was 1, 2, 3, 4 wide, so I need to go 1, 2, 3, 4 wide. There's A prime. Now, if Kevin does not understand how I did that, especially since my colors are not showing up very nicely this morning, turn off the lights. If Kevin does not understand how I did that, especially since my colors are not showing up this morning, he can seriously pick up each point and use that translation vector on it. So he can pick up C, move it right 2, down 1, 2, 3, 4. Pick up B, right 2, down 1, 2, 3, 4. I just don't take the time to do that because once you know the one, the rest are kind of easy to figure out if it's an easy shape like a rectangle. Okay, are there any questions about that example? I didn't think so. Okay, next it says translations in the coordinate plane. A vector can be used to translate a figure in the coordinate plane when written in the form, and that's our translation vector, AB, with brackets, little pointy arrows, where A represents the horizontal change, B represents the vertical change. And to translate, the new points are X plus A, Y plus B. Meaning, if we were wanting to be specific, because Harrison does not like my counting technique, he likes to actually list ordered pairs. If he wanted to figure out A prime, he would add those two together. 1 plus 2 is 3. He would add those two together. 2 minus 4 is negative 2. And if he looked over at our graph, lo and behold, we actually did put A prime at 3, negative 2. Same thing with B prime. You could add that translation vector to each coordinate. So 1 plus 2 is 3. 4 minus 4 is 0. Oh my goodness, we did put B prime at 3, 0. So if you want to figure out the coordinates, you can. Okay, moving on. It says graph the triangle TUV with vertices. Well, they're so nice, they already did it for us. Along the vector negative 3, 2. So what does that negative 3 mean? If this is our translation vector, what does that negative 3 mean? What does that positive 2 mean? So I'm going to pick up a point and move it left 3 up 2. Now this is not an easy one to count because we got to get it just so. So I probably need to pick up and move each point. So let's see. U left 3, 1, 2, 3, up 2, 1, 2. There's U prime. T left 3, 1, 2, 3, up 2, 1, 2. There's T prime. 1, 2, 3, up 2. There's V prime. And of course I need to do my best to connect those dots, which is apparently a struggle this morning. And there's my translated image. Okay, does anyone have any questions about that one? Well, you know, we couldn't just leave life easy and only do triangles and rectangles. We got to try some other shapes too. So our last example for translations is a pentagon, and of course it's named penta for its 5 points. So we need to graph P is at 1, 0. E is at 2, 2. N is at 4, 1. Good morning. Go for it.
I'm going to put the lights on you.
Go for it.
What you had.
I forgot what I was doing. I was graphing the pentagon. How is it going? Good. Well, that was exciting. Okay, way more exciting than graphing this pentagon. T is at 4, negative 1. A is at 2, negative 2. Cute little pentagon. Again, on the test on Friday, there are, I think, 4 where you actually do it yourself, but most of them are multiple choice. So it's you spotting, did they do the right thing? Okay, so that was our original. Now we need to make our new image. We need to look at our translation vector. What does that negative 5 tell me to do? What does that negative 1 tell me to do? So I need to pick up each point and move it left 5 and down 1. So let's see, if I pick up P, 1, 2, 3, 4, 5, down 1. There's P prime. 1, 2, 3, 4, 5. Okay, is there anyone who's having any troubles with these translations? This is how Kevin can blow it. 1, he cannot do it at all. 2, suddenly his pentagon turns into a rectangle, a triangle, anything except a pentagon. And he can't twist around the pentagon in any way, because when we do a translation, we're literally moving the shape left, right, up, down. We're not twisting it in any way. Okay, if there aren't any questions, if you look on the back, there are a couple for you to practice, and to me, it looks like a Tetris game. So on the back, on the Tetris game, they wrote the vectors weird. -3, 0 is the vector -3, 0. I don't know why they wrote it funky. So 0, 4 is really 0, 4 as a translation vector. So we're not moving any left or right, we're moving 4 up. But to me, it reminds me of a Tetris game. So you need to take each of the Tetris shapes and move them the way the translation vector wants. Are there any questions about that? Okay, I'm going to give you about 5 minutes on that, and then I'm going to start talking something else at you. So, here's your chance. I think reflections are actually the hardest. I think translations are the easiest, and rotations are about the medium. However, I say all that, and most people, if you're going to make a mistake, they make a mistake on rotations. Okay, so the reason people make a mistake on rotations is because they forget who to swap when. Sounds crazy, but it's true. A rotation is when we turn something around a fixed point. You can't see what I'm doing. When we turn something around a fixed point, like if I turn my notes around the fixed point my pen is making, we turn it around. You stare at a rotation all day when you stare at the clock. So that fixed point is called the center of rotation. So the top of the notes is center of rotation. Now you actually don't have to identify where that center occurs, which is weird because you had to identify where that line of reflection was. Strange. Okay, so I'm actually going to go completely out of order. I want to go to the first example I want to do is number 3. And it tells you how we're rotating. I'm picking number 3 because it says we're rotating with 180 degrees. That's why I'm picking it first. Okay, so I need to plot the points for this triangle. It says -3, 5. Oh, but what's really annoying is this coordinate plane is counting by 2. So -3 is there. 5 would be here, so -3, 5. That's terribly annoying. No one has time for that. B is 0, 2. C is -5, 1. So we've got our triangle, our original triangle, and we need to rotate it 180 degrees. When you turn something 180 degrees, what happens to it? Does it stay the same? I thought 360 was all the way around. So if I'm going to turn 180 degrees, how do I turn? Do I go here? I think that's 90. I think this is 180. So you saw my front. If I do a 180 degree turn, I think you see my back, right? Right. You agree? In the same way, we've got to do the exact same thing to all our points. So everybody becomes negative. So it was -3, 5, our A prime is going to be 3, -5. B used to be 0, 2. When we turn him around, well, there's no such thing as -0, but it would be 0, -2. What would C prime be then? 5, -1. So 180 degrees, everybody gets changed. We change everyone's sign, or we multiply everybody by -1. Okay, so if I'm to graph this, A prime is at 3, 5. B prime is at 0, -2. C prime is at 5, -1. And our shape really does look like you turned it around, like you did something to it. Did I do that wrong? It does look bigger. Let's see. At what point did I graph incorrectly? 3, -5. Thank you, Kevin. Kevin is correct. I can't graph today. The good news is I get stuff in the notes. A was 5. And I grabbed the wrong set. So I was supposed to do 3, -5, 0, -2. C prime was supposed to be 5, -1. That looks much better. No, if only my original was there. And if only you could see it. Okay, and now it actually looks like the shape turned around because A was on top and now A is on bottom. That makes sense. You turned around. You turned the shape around. Are you good with that 180? Are there any questions on 180? Well, Harrison's no dummy. He's already looked at the back. He sees that there are 6 problems he has to do. Number 4 and number 5 both say we're rotating 180 degrees. So if you're looking at the worksheet on the back, 4 and 5 are 180 degrees. So on 4 and 5, you need to change the signs of everything in every coordinate. So for instance, D would be 4, -3. D prime would be. Okay, well if you're good with that kind of a rotation, then we've got to do 90 and 270. So 90 is like you gone halfway this way. 270 is you gone halfway the other way. You can see why people start to get those a little confused. So for 90, we'll do that first. If you read the directions, it says multiply the y coordinate by -1 and interchange the x and y coordinates. Okay, so we're going to interchange them and multiply the y coordinates by -1. So I'm going to go ahead and change all the y coordinate signs. Zoom in on that. And interchange them. So that means f prime is -7, 7. G prime is -2, 9. H prime is -2, 3. And I prime is -7, 5. Now if I quickly graph these, my first trapezoid was at 7, 7. 7, 7. There's F. G was at 9, 2. H was at 3, -2. I swapped them, so I changed all the coordinates. Negative, 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 negative on all the y's, and then I swapped them all. So it became -7, 7, -2, 9, -2, 3, -7, 5. You change the sign on the y, and you swap them.
You always change the y.
If it says 90 degrees, yes. We're going to do the exact opposite on 270. We're going to change all the x's to negative, and then swap them. F, G, H, and then I is at -7, 5. Okay, I'm going to stop my graphing rant. I swear I will come back to graphing this, and we'll probably have to discuss this whole thing again tomorrow. But Jarrell said something smart, and I want to hit on that now. The difference between 90 and 270 is that 90, we change the y coordinate, and then we swap them. On 270, we're going to change all the x coordinates, and then swap them. So, for instance, P prime is going to be 7, -4. Q prime is going to be 6, -6. R prime is going to be -2, -3. and S prime is going to be negative 1, negative 1. So the difference between 90 and 270 is you're changing the signs of somebody and you're swapping somebody, and that's where people make a mistake. For 90, you change the sign of the Y's. For 270, you change the X's. Now, I will come back to this exact one tomorrow, and we will graph it again, and we will go back over this really quickly, but I swear we don't have that much time to spend on it tomorrow, so you probably want to go ahead and get all the homework problems for it done today if you could. Okay.